Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will be talking about Raman effect under the paper Atomic, Molecular and Laser Spectroscopy. We will be able to learn in this module the introductory of Sir Chandrasekhar Venkat Raman, Raman effect, effect of light scattering, classical theory of Raman effect, limitations of the classical theory and quantum theory of Raman scattering. Why the Stokes lines are higher in intensity than the anti-Stokes lines? Setup used for Raman effect, etc. A brief about Sir Chandrasekhar Venkat Raman will be quite important to understand his motivation, that he was born in 1888 in a village in southern India. As a child, Raman was precocious, curious and highly intelligent. His father was a college lecturer in mathematics, physics and physical geography. So the young Raman had immediate access to a wealth of scientific volumes. By the age of 13, he had read Helmholtz's popular lectures on scientific subjects. Raman was deeply interested in music and acoustics. While in college, he read the scientific papers of Lord Rayleigh and his treatise on sound, as well as the English translation of Helmholtz's The Sensations of Tone. This initiated Raman's later interest in the physics of drums and stringent instruments such as the violin. He used fine chalk powder and photography to investigate the vibrational modes of drums. The white chalk remained only at the nodes of the vibrating membrane. The phenomena is named after the great Indian physicist Sir Chandrasekhar Venkat Raman, who first published observations of the effect in 1928. When a parallel beam of monochromatic light goes through a gas or liquid or transparent solid, a part of light is scattered in all directions. It may be reflected, absorbed or scattered in the same manner. The intensity of scattered light is inversely proportional to the fourth power of wavelength. It is found that the scattered light contains exactly the same wavelength as the incident light. This scattering is called the Rayleigh scattering, and we refer it to elastic scattering. Apart from this wavelength, the scattered light also contains some weak additional lines. As said earlier, that this phenomena was first discovered by Raman and his collaborators and is known as Raman effect. A comparison of the wave numbers of these additional lines shows that these Raman lines are independent of the wavelength of the incident light, but depends on the nature of scattering substances. For different scattering substance, the displacements of the Raman lines from the incident light are different. Thus, the displacements are characteristics of the scattering substance. Raman spectroscopy studies the frequency change of light due to the interaction with matter. The energy of a vibrational mode depends on molecular structure and environment. Raman signal is weaker than the incident light. Photons are not absorbed, and to observe Raman scattering, the molecules must be polarizable. How Raman measures the effect of light scattering? It is the scattering of the radiation that occurs and gives information about molecular structure. Analysis of light scattered by a liquid is not an easy task, and much of the early work in Calcutta was done by the visual observation of the color rather than precise measurements of the light's wavelength, as has been depicted in the figure. The fundamentals of Raman crucial experiments have been outlined in figure 2. There are various components. The main is the sunlight, then it is filtered using the violet filter, then there is a scattered liquid, and the observers the green wavelength filtered through the green one. Most of the light emerging from the liquid sample is of the same color as the incident violet beam, the so-called Rayleigh scattering light. However, Raman and his co-workers, K.S. Krishnan particularly, were able to show that some of the scattered light was a different color that they could isolate by using a green filter placed between the observer and the sample. The advantage of using a visual observation is that several substances can be studied quickly. In his first report to Nature, titled "A New Type of Secondary Radiation," Raman indicated that approximately 60 different liquids had been studied and all showed the same result. Some scattered light had a different color than the incident light. It is thus, Raman said, a phenomena whose universal nature has to be recognized. When light passes through a transparent medium, then scattering of light takes place, as well as light undergoes a change in frequency and random alteration in phase due to a change in rotational or vibrational energy of the scattering molecules, which is called Raman scattering. Thus, Raman spectroscopy is the intensity analysis of Raman scattered monochromatic light as a function of frequency of the scattered light. There is a classical theory to understand. The classical theory of Raman spectroscopy for molecules is described as a group of atoms performing simple harmonic vibrations without taking into account the quantization of the rotational and vibrational energy levels. According to the classical theory, the incident electromagnetic field induces an electric dipole moment of scattering system. Molecule or solid, anything can be a scattering system. Such an induced dipole moment is oscillating with the frequency of the incident radiation and is acting as a secondary source for electromagnetic radiation. The light is scattered in all the directions. Now, if E is the electric field strength, then time varying electric field is written as E is equal to E naught cos of omega naught t. E naught is the vibrational amplitude of electric field, omega naught is angular frequency, it is 2 pi nu naught, where nu naught is the frequency of laser light or any other light source being used. Therefore, equation 1, E is equal to E naught cos of 2 pi nu naught t. Induced is given by mu is equal to alpha E. Using equation 2 in equation 3, thereby replacing E with E naught cos of 2 pi nu naught t. According to laws of classical electrodynamics, an oscillating electric dipole emits radiation of the same frequency at which the dipole oscillates. If the polarizability alpha doesn't change with time, that means alpha is constant, then the induced dipole will re-emit the incident radiation of the same angular frequency. If the molecule is vibrating with a frequency nu, then nuclear displacement Q can be written as Q is equal to Q naught cos of 2 pi nu t. Here Q naught is the vibrational amplitude. If the vibrational amplitude is small, then polarizability can be expanded in a Taylor series around its equilibrium position. Alpha is equal to alpha naught plus curly alpha upon curly q, q plus the higher order terms are there. Alpha naught is the polarizability at equilibrium position, and curly alpha upon curly q at nu is equal to 0 is the rate of change of polarizability with respect to nuclear displacement q and evaluated at equilibrium position. Using equation 5 and 6, equation 4 can be rewritten as mu is equal to alpha naught plus curly alpha upon curly q, q naught cos of 2 pi nu t plus the higher order terms into E naught cos of 2 pi nu naught t. And neglecting the higher order terms and concentrating only on the two terms, mu is equal to alpha naught E naught cos of 2 pi nu naught t plus curly alpha upon curly q, q naught cos 2 pi nu t, E naught cos 2 pi nu naught t, which is equal to alpha naught E naught cos 2 pi nu naught t. First term remains the same. Second term can be applied in little trigonometrical relation. Half of curly alpha by curly q, q naught E naught cos 2 pi nu naught plus nu t plus cos 2 pi nu naught minus nu t, which is further equal to, separating all the terms, we get three terms: alpha naught E naught cos 2 pi nu naught t plus half alpha curly alpha upon curly q, q naught E naught cos 2 pi nu naught plus nu t plus half curly alpha upon curly q, q naught E naught cos 2 pi nu naught minus nu t. First term represents a Rayleigh scattering, which is alpha naught E naught cos of 2 pi nu naught t. The second term, half alpha upon curly q, q naught E naught cos 2 pi nu naught plus nu naught t, represents the Stokes Raman scattering. While the third term, half curly alpha by curly q, q naught E naught cos 2 pi nu naught minus nu t, represents the anti-Stokes Raman scattering. As it is known that classical theory of electromagnetism states that an oscillating dipole emits radiation of the intensity I is equal to nu naught 4 upon 12 pi epsilon naught c cube mu square. The incident intensity of light is proportional to E naught square, and Raman scattering intensity is given by I scattering proportional to mu naught square is equal to curly alpha by curly q square I naught square. A small portion is in elastically scattered Raman scatter composed of Stokes and anti-Stokes portions. Limitations of the classical theory. The classical theory gives very good agreement for Rayleigh scattering and vibrational Raman scattering on frequency dependence. Classical theory is good enough to obtain characteristic molecular vibrational frequencies and use them as molecular signatures in the qualitative analysis. However, the classical theory has many limitations. It cannot be applied to molecular rotations, as classical theory does not ascribe specific discrete rotational frequencies to molecules. And classical theory cannot provide information as to how polarizability is related to the properties of the scattering molecule, in particular its characteristic transition frequencies and to the frequency of the incident radiation. The quantum mechanical theory provides this information and forms the basis for a complete treatment of all aspects of Raman scattering. Quantum mechanical treatment discloses that Raman scattering is a powerful and versatile tool that can be used to determine molecular parameters and to explore some detail of the spectroscopic properties, not only of the ground electronic state but also of the electronic upper state of the molecules. It is noteworthy that every compound or molecule has its Raman spectra characteristics that help to further identify the molecules in even some devices for many applications. Quantum theory of Raman scattering. When the incident light of frequency nu collides with a molecule, it is either scattered elastically or inelastically. The light quanta can add or subtract from the system the amounts of energy equal to the energy difference between the stationary states of the system, and let delta E be the energy difference between two levels. If the system is initially in the lower state and is brought to the upper state by scattering of light quanta, the energy delta E being subtracted from the light quantum. This scattering of radiation is two-step process. Step 1, photon of energy h nu is absorbed, exciting the molecule from the lower state Ea to some upper state Em. Step 2, the molecule emits a photon of energy h nu minus delta E and is de-excited from the upper state Em to some final state Eb. The two steps can occur in reverse order. That is, the photon of energy h nu is absorbed by the molecule, raising it from excited state Eb to state En, and molecule emits a photon of energy h nu plus delta E and is de-excited from state En to lower state Ea. If the final state Eb of the molecule is the same as the initial state Ea, the emitted radiation has the same frequency as the incident radiation. This process is called Rayleigh scattering. If the final state is different from the initial state, the scattering is inelastic and law of conservation of energy gives h nu prime is equal to h nu plus minus Eb minus Ea. This inelastic scattering process is called Raman scattering or simply the Raman effect. Now, if nu prime is less than nu, the observed line is called Stokes line, and for nu prime greater than nu, the observed line is called anti-Stokes line. The intermediate state Em or En need to have opposite parity to the state Ea and Eb for the electric dipole transition to take place. Thus, Raman scattering does not change the parity of the molecule. Raman effect can take place for any frequency of the incident light. Raman effect does not require the presence of a permanent electric dipole moment, but rather an induced dipole moment developed under the electric field of incident radiation, and therefore Raman lines are observed for homonuclear molecules like hydrogen molecule, oxygen molecule, etc., that do not exhibit pure rotational or vibrational spectra. The Raman and infrared spectra are complementary to each other because of different nature of the processes involved in the two effects. Raman process is a scattering effect involving an induced dipole that depends on the change of molecular polarizability during vibration, while infrared spectroscopy is an absorption process caused by the change in the permanent molecular dipole. According to quantum theory, the Raman effect is the outcome of the collision between the light photon and molecules of the substance. Suppose a molecule of mass m in the energy state moving with a velocity v and is colliding with a light photon m. Let this molecule undergoes a change in its energy state as well as in its velocity. Let this new energy state be and the velocity v prime after suffering a collision. If we apply the principle of conservation of energy, one can write Ea plus half mv square plus h nu is equal to Eb plus half mv square plus h nu prime. The change in velocity of molecule is practically negligible. Ea plus h nu is equal to Eb plus h nu 1, or we can find out nu 1 is equal to nu plus Ea minus Ev upon h, or nu 1 is equal to nu plus delta nu. Now, three cases arise. If Ea minus Eb, the frequency difference is 0, it means that nu 1 is equal to nu, and this refers to the unmodified line where the molecule simply deflects the photon without receiving any energy from it. This collision is elastic and is analogous to Rayleigh scattering. If Ea minus Eb, that means nu prime is greater than nu, that refers to the anti-Stokes lines. It means that the molecule was previously in the excited state and it transferred some of its intrinsic energy to the incident photon, and thus the scattered photon has greater energy. If Ea minus Eb is such that nu prime is less than nu, this corresponds to Stokes lines. This molecule has absorbed some energy from the photon, and consequently the scattered photon will have lower energy. A change in the intrinsic energy of the molecule is governed by the quantum rule, as Ea minus Eb is equal to plus minus n h c. N can take the values 1, 2, 3, etc., and nu c is characteristic frequency of the molecule. So, when n is equal to 1, nu 1 is equal to nu plus minus nu c. and frequency difference between the incident and scattered photon in the Raman shift corresponds to characteristic frequency nu c of the molecule. Now, considering a system where E naught is the ground electronic state and nu double prime is 0, 1, etc. are the vibrational states of the ground electronic state. If the light frequency nu naught is allowed to incident on this system, the three cases arise. Case 1. Molecules absorb the light of frequency h nu 0 and go to the vibrational state, as can be seen in the figure. The vibrational state is created by the light and molecular interaction and exists as long as the light exists. It is not the eigenstate of the system, but is a linear combination of all the eigenstates of the molecule. The lifetime of this virtual state is quite small, and the molecule will be back to the ground vibrational state nu is equal to 0 and will emit the same frequency nu 0. This is the same as Rayleigh scattering. Case 2. Molecules are transferred to the vibrational state by nu 0 light, and these excited molecules may come back to the higher vibrational state nu double prime is equal to 1. In this case, the emitted frequency is nu 0 minus nu. According to energy conservation, the energy will be lost from the incident photon energy h nu 0 to excite the vibrational frequency of the molecule, and thus the emitted photon energy is h nu Stokes, h nu 0 minus h nu nu. Case 3. In thermal equilibrium, the excited vibration levels are also populated, and molecules there can also absorb light and go to virtual state. While coming back to the same vibrational state, this will emit frequency nu 0. But if molecules come back to ground vibrational state nu is equal to 0, then the emitted frequency will be nu 0 plus nu nu. Again, according to law of conservation of energy, the photon energy adds up to the vibrational energy, and emitted frequencies will be h nu anti-Stokes is equal to h nu naught plus nu naught. Why these Stokes lines are higher in intensity than the anti-Stokes lines? The population to these vibrational states depends on the Maxwell-Boltzmann distribution. The origin of anti-Stokes lines is from the higher vibration levels, and the population is lower in those states than the ground vibration level. As the intensity of transition lines not only depend on the transition probability but also depend on the propagation of the initial state. This is the reason for the lower intensity of anti-Stokes lines than the Stokes lines. There is a setup for observing the Raman effect. This system consists broadly of 4 major components: excitation source, where nowadays the laser is used, sample illumination system and light collection optics, and then wavelength selector. It can be filter or some spectrophotometer, and then there is a detector. Nowadays, charge coupled devices, CCDs or photodiode arrays are used, although there was a concept of using photomultiplier tube. A sample is illuminated with the laser beam in the ultraviolet, visible or near infrared range. Scattered light is then collected with a lens and is sent through interference filter or spectrophotometer to obtain Raman spectra of the sample. The main difficulty of Raman spectroscopy is separating it from the intense Rayleigh scattering, as spontaneous Raman scattering is very weak. It is also noteworthy that the intensity of stray light from the Rayleigh scattering largely exceed the intensity of the actual Raman signal in the proximity of the laser wavelength. The remedy is to simply cut off the spectral range close to the laser line, where the stray light has the most prominent effect. The commercially available interference or the notch filters that cut off spectral range of plus minus 80 to 120 centimeter inverse from the laser line. This method is efficient in stray light elimination, but it doesn't allow detection of low frequency Raman modes in the range below 100 centimeter inverse. The source of generation of stray light is light dispersion on gratings, and hence depends on grating quality. The modern Raman spectrometers use holographic gratings, as the Stray light produced by holographic gratings is about an order of magnitude less intense than from ruled gratings of the same groove density. Single point detectors such as photon counting photomultiplier tubes have been used since long, but the advancement in technology has replaced the detector to multi-channel detectors like photodiode arrays or charge coupled devices. So let us summarize what we have learnt in this model, that Sir Chandrasekhar Venkata Raman leads to the invention of the Raman effect and hence achieved the Nobel Prize. The frequency change of light due to the interaction with matter is called Raman effect. In classical theory, the incident electromagnetic field includes a electric dipole moment of scattering system, and molecule or solid, anything can be scattering system. Such an induced dipole moment is oscillating with the frequency of the incident radiation and is acting as a secondary source for electromagnetic radiation. As the intensity of transition lines not only depend upon the transition probability but also depend upon the population of the initial state. That is why the intensity of anti-Stokes lines is of lower intensity than that of the Stokes lines. Thank you.